I give you the second definition of the cross product, that we having two vectors A and B. The angle between these two vectors is theta. So the definition of the cross product is A cross B is equal to magnitude of A into magnitude of B into sine of theta. So you say this is also the scalar, this is magnitude of A, magnitude of B, and sine of theta. And we have the direction of this one, that this is the direction of A cross B is given to this one is the n. The direction vector is n. No, this is a vector because having the magnitude and also the direction. So we say this vector A cross B is orthogonal to the plane containing A and B. A cross B is orthogonal to plane containing vectors A and B, and our angle theta, that is between 0 to pi. This is the domain of theta. This is from 0 to pi, and this is our cross product. And here we can see conclusion of this one, as we have already seen in the last definition, that they are orthogonal. This means here this A cross B is orthogonal to B, and A cross B is orthogonal to A. If they are orthogonal, then we are having here number one, A cross B dot A is equal to 0. Then we say here what's the result? The result is that A cross B is orthogonal to A. And the second one is that we are having here number 2, we are having A cross B dot B is equal to 0, the dot product. When the dot product is 0, then we can say that A cross B is orthogonal to B. You can see it here. If this angle is 0, then A and B are parallel. When this is 0, then we are having A cross B equal to 0. This is number 3. Number 3, if you take the cross product, and the cross product is equal to 0, then we say A is parallel to B as theta is 0. When theta is 0, then sine 0 is 0. We have already seen this result before, that in the case of the dot product, when A dot B is equal to 0, then we say A is orthogonal to B. So that we have already done in the dot product. In cross product, when A cross B is 0, then A is parallel to B. So that's the ideas we get it from here. Now we having that is having the magnitude and also the direction. The direction we have seen. Here, what's the magnitude? Magnitude is AB sine theta. Before doing this magnitude, we see some definitions here that you know. For example, I have the rectangular here. This is my rectangle, and this side is my x, this side is my y. What's my area? My area is equal to area of the rectangle is xy. If I'm having a parallelogram, this is my parallelogram. This is my x. Now I take the height. So what's the area of this one? Area of the parallelogram. Area of the parallelogram is x into h, where h is the height. So that's the parallelogram. Now when I take this A and B, this is my A and this is my B. This is my A and this is my B. They are side of the parallelogram. I complete the parallelogram. So I complete this parallel to A here and parallel to B here. So this becomes a parallelogram. And we can find the height of the parallelogram. When we want to find the height of the parallelogram, this is my angle theta. So the component of B along A is cosine theta, and opposite to A is sine theta. So this I say, this might be sine theta. Now when I take the length of this one is magnitude of A, that's magnitude of A magnitude of the vector A. So what's the area? Area is magnitude of A multiplied by the height. My height, this is my height. Height is equal to B sine theta. So number 5, I can find here the area of parallelogram made by vectors A and B. So as I shown you here, then having area is equal to magnitude of A cross B, because what is having, I am having a magnitude of A into magnitude of B into sine of theta. So this is my height and this is A is my length. So if I draw it here again, this is my parallelogram, and this is my vector B, this is my vector A, this vector B, this vector A. So length of this vector is magnitude of A, and this angle is theta between them, and this height of this one is I denote by h, and h is equal to B sine theta. So that gives me the area of the parallelogram made by vector A and B. Then we have a very nice or very interesting definition. That's the area of the triangle. Area of triangle made by vectors A and B. A and B. So if I have this vector, this is my vector A, and this is my vector B, this is my vector A, this is my vector B. I say this is my A, this is my B, and I join this one, this is my C. So you can see here, if I divide this one too, if I make it complete this one, and this one will be my parallelogram. So what am I taking? I'm taking half of that one. So we say that when we want to find the area of the triangle ABC, so area of triangle ABC, area of triangle ABC is equal to 1 by 2 magnitude of A cross B. That's magnitude of the parallelogram. So that's the idea that we can find here, the area of the parallelogram, area of the triangle. If I want to find the unit vector, log A unit vector orthogonal to the plane containing AB, simply I take the magnitude of this one divided by this one, that give me the unit vector. So if I want to find the unit vector here, I have the plane containing A and B. I say I want to find this number 6, number 5, number 6, number 7. Unit vector orthogonal to plane. This is very important concept because we'll be using this one in coming articles. Plane containing A and B. What is that? This is my unit vector U. This is my vector orthogonal to A and B. I divide by its magnitude. That gives me the unit vector. I denote by N. Instead of U, I denote this by N. This is my unit vector orthogonal to the plane. I have seen it here. This is my N. This is orthogonal to this along the A cross B. This was the direction of, this gives me the direction. This is the direction of vector A cross B. This is the direction. And this was here, this was the magnitude. This is parallelogram was here, this was the magnitude of the vector. Magnitude of the cross product of A cross B. This was the magnitude, and that is the direction of A cross B. We will apply this concept to do some of the problems.